So far, we've seen two properties of the real numbers, the field properties and the order properties. In this video, we're going to talk about the last of the three properties we're using to characterize the reals, which is the completeness property. The big difference here is that the algebraic properties and the order properties were shared by the reals and the rationals. The completeness property is really what makes a difference, and it tells us how the rationals sit inside of the reals. Before we can say it carefully, we need a few definitions which are sort of straightforward. The first ones are related to upper bounds and being bounded above. So if E is a collection of real numbers, a real number M is called an upper bound for E if X is less than or equal to M for all X in E. So what does that look like? So you have some set of the real numbers E, which looks like this, say an interval, and then an upper bound is some number M, which is sitting to the right of the interval. It could be sitting right on the boundary, it could be sitting far away, it could be sitting very far away, but it's sitting somewhere to the right. We say that a set E has an upper bound if there exists some M which has this property, and then we say that it's bounded above, and if not, we say that it's not bounded above or it's unbounded above. So what are the sets that are not bounded above? Well, the real numbers as a whole aren't bounded above, right? There's no number M that's bigger than all of the reals, okay? There's an analogous collection of definitions for lower bounded and bounded below, and it's exactly the same thing, but on the left-hand side. If you're both bounded above and bounded below, then we say that you're bounded, or bounded in both directions. Okay. So far I hope so good. Another piece of jargon that we need is the maximum element or the largest element. And so if E is a set of real numbers and M is an upper bound for E, if E is a set of real numbers and there exists an element M that's an upper bound for E, then we call M the maximum, okay? So what's sort of the idea there, right? If we have a set E, which looks like a closed interval, then this top number M is the maximum element of E, okay? Then we have an analogous definition for the minimum or the smallest element. Now, it's worth saying very quickly here something that I think is sort of clear, but we don't necessarily think about very much, which is that not every collection of elements has a maximum. Now, there's sort of a boring way not to have a maximum. If you're looking at the real numbers, then you have no upper bound, so obviously you have no maximum as well. But there are other ways to fail to have a maximum. And so let's compute the minimums of a couple of sets. So if I have the finite set 1, 2, 3, so it's just 3 elements, well, then it's clear you have a minimum, and the minimum goes 1. If I look at the interval from 1 to 3, well, it's maybe not 100% obvious what the minimum is, or that a minimum exists, but we could sort of guess what the minimum should be, and it's 1 as well. So that's sort of okay, and that's true, although I'm not going to carefully prove it right now. I'll prove something very closely related in a second. If we have the open interval from 1 to 3, that is, all real numbers that are strictly bigger than 1 and strictly less than 3, well, then it's not so obvious what the minimum is supposed to be. There's sort of a natural guess, right? The minimum should be 1, just like it was for the other sets. But if you look at the definition for a minimum, we need the prospective minimum to actually be in the set. So 1 isn't in the set, and so 1 can't possibly be the minimum. Okay, if you look at another number, though, for example, if this was 1.1, well, obviously that can't be the minimum, because 1.05 is in 1.3, and 1.05 is less than 1.1. And you can sort of convince yourself by looking at this for a few seconds that whatever number I'd written down here, you can play the same game. Let's try to formalize that. Let's say that X is in 1.3. I want to check that X actually can't be the minimum, and here's one way to do that. You define Y to be 1 plus X over 2. That's in the interval 1, 3, and Y is strictly less than X. So this little calculation here is actually a quick proof that this set doesn't have a minimum at all. To go over that again, let's assume the set does have a minimum, say X. Then there's this other element Y, which is halfway between X and 1, which is definitely still in the set, and furthermore, it's definitely less than X. And so this set doesn't have a minimum. So there are a couple of ways for a set to fail to have a minimum. One is obviously if it's unbounded, it has no minimum. But second of all, if it's sort of an open interval like that, then it can also fail to have a minimum. And there are all sorts of more exotic sets which aren't open sets or closed sets, and many of them also fail to have a minimum. for sort of the same reason that this sort of open interval doesn't have a minimum. All right, I'll continue in a second, but I need one little notational aside. I often talk about open and closed intervals, and since we're still talking about axiomatic systems, it's useful to say, well, what do I really mean when I say that interval in the language of the real numbers? This closed interval a, b, that's all elements x and r which are greater than or equal to a and less than or equal to b, and the open interval, that's all elements x and r which are strictly bigger than a and strictly less than b. Okay? Why is that different from your usual definition? Well, it's going to agree with your usual definition, but I've written things just in terms of operations that we already have, in particular, just in terms of ordering. Okay? So you don't have to think about that too much, but it's sort of useful to say, hey, we have this notion of an interval that doesn't require anything besides this sort of comparison. All right, so minimums and unboundedness and minimums and bounded sets and so on are all, I think, probably fairly familiar. But here's a new definition, which I think is probably not a word that you've seen before, which is the supremum and its twin, the infimum. So I'm just going to read the whole thing because it's worth looking at very carefully. Suppose E is a non-empty set of real numbers. If M is an upper bound of E, so that M is less than or equal to M prime for all other upper bounds M prime of E, we say that M is the supremum or least upper bound of E. And we write M is equal to sup of E. We have a similar definition for infimum, that is, it's a lower bound, which is bigger than all of the other lower bounds. So it's a picture that looks like that what we're looking at when we're looking at the supremum. Let's look at the interval 1, 3, and then an open interval again. So we've seen already this doesn't have a minimum, and also it doesn't have a maximum. But certainly it's bounded, right? You're only looking at numbers from 1 to 3, so it has a whole lot of upper bounds. So one of them, for example, is 12 is an upper bound, and 4 is an upper bound. But also you can get very close to 3, and 3.1 is an upper bound. And actually, 3 itself is an upper bound, right? 3 isn't in the set, but it's certainly an upper bound. Something that you can probably convince yourself of fairly easily is that 3 is the smallest upper bound. If I look at all of the upper bounds, that's some set, and 3 is the smallest element of the set, and we'll see in a second that means it's the supremum. So that's all that's going on here when you're looking at the supremum is you look at the collection of upper bounds. In this case, we can write it down. It's a set from 3 to infinity. And the supremum is just the smallest element of that set. Infimum is the same thing on the other side. When we're talking about supremums and infimums, it's useful to have a little bit of extra notation. If you have an empty set, we say that the infimum is infinity and the supremum is minus infinity. If you're unbounded above and non-empty, the supremum is plus infinity. If you're non-empty and unbounded below, then the infimum is minus infinity. That's just sort of a handy little bit of notation, which is going to be useful later on when we want to write sort of comparisons between infima and suprema. This notational convention lets us write down lots of those without sort of writing down lots of special cases. And that's really where these conventions are coming from. Okay. So as I said, and as we'll prove in a second, the infimum is sort of not very hard to compute if you look at a nice set, and particularly the infimum of 1, 3, the open interval, is going to end up being 1, but I'm going to defer that just for a moment and defer all calculations and get to sort of the main part of today's video, which is the completeness axiom. And the completeness axiom says the following: every non-empty set of real numbers that is bounded above has a least upper bound, and there's a corollary which is sort of equivalent. Every non-empty set of real numbers that is bounded below has a greatest lower bound. In other words, even though maximums and minimums don't necessarily exist, supremums and infimums, they always do exist. All right. What does that have to do with talking about the real numbers and the rationals? Well, this is basically how we fill in the holes in the rationals. So the rationals, most numbers are not rational, but they're sort of everywhere along the real number line. And what are the real numbers? Well, we take collections of the rationals, we sort of add in all of these least upper bounds and greatest lower bounds, and when we add in those extra numbers, it turns out those are actually the real numbers. So that's the idea of what's going on here. We're going to be using this property a whole lot. This completeness axiom is more or less what distinguishes the reals from the rationals, and so it shouldn't be terribly surprising that we need it a lot in most of the rest of this course. We're not going to do it in any sort of serious way right now, but at least we'll do a little calculation. I will say that I've written this as an axiom, not as a theorem. Now, there's something a little bit funny there, right? Obviously, at some point, somebody has to do the work to check, hey, it actually makes sense to talk about real numbers satisfying this rule, but we're not going to be doing that in this course. We're just going to assume that this is given, that all all non-empty sets of reals that are bounded have least upper bounds. Let's at least calculate the infimum or the supremum of something. So I said before that the infimum of the open interval 1, 3 should be exactly equal to 1. So how do you check something like that? Well, one direction is easy. It's clear that for every x between 1 and 3, 1 is less than or equal to x. Why is that clear? Well, that's really the definition of 1 and 3, right? So that part's clear. If 1 is less than x, that 1 is less than x for every element x in the interval 1, 3. So 1 is definitely a lower bound. Then we need to check, hey, is it the greatest lower bound? In other words, is it possible that there's another lower bound that's bigger than 1? So how do you check something like that? Well, the usual step is to assume not, so there exists some y bigger than 1 that's also a lower bound. I'm going to pause the proof for a second and just say, well, that seems a little bit silly, doesn't it? I mean, we can draw the real numbers, right? We have 1 that's here, we have 3 that's here. How could there possibly be another lower bound that somehow would be sitting just to the right of that interval, right? We know that there's a solid line here. And it's true, we do know that there's a solid line there, but somehow we actually have to do at least a little bit of work to check. And one way to convince yourself that this isn't a completely silly thing to say is to point out that actually if we weren't dealing with the real numbers, if we were dealing with some other collection, some other number system or some other collection of numbers, that in fact it's quite possible that there would be a bigger number there. So let's make that a little bit formal just to have this collection of examples in mind. I define the open interval 1, 3 with respect to some set S to be the collection of all elements of S so that 1 is less than x is less than 3. So this is exactly the usual definition for the open interval, except that I'm saying I'm living inside of some other collection of numbers, this set S. And so what's this open interval 1, 3 with respect to the naturals? Well, it's just the element 2. So in particular, like 1.5, 1.9, 2 are all lower bounds if we're only looking at the naturals. Okay, so for the naturals, at least, there really are greater lower bounds. And the reason that can happen, of course, is that for the naturals, there are these enormous holes in the line, right? And so if you're bigger than 1, well, there's sort of not a lot, there are a lot of things that are missing that are bigger than 1. All right. Now we know that that doesn't happen for the reals, but we have to check it, and that's what we're about to do after that long digression. So let's assume that 1 is not the greatest lower bound. So in particular, there's this other number y that's also a lower bound. How are we going to check that there's a problem? Well, we're going to look at, first of all, I'm going to be a little bit silly. I'm going to find z to be the minimum of y and 2. Okay. So if y is a lower bound, then definitely the minimum of y and 2 is also going to be a lower bound, right? It's smaller than y. So I just want to assume that y is less than or equal to 2, so I can do the next bit of the calculation. And then what do? I define a to be z plus 1 over 2. And the thing that I notice is that, first of all, a is strictly, 1 is definitely less than a, because 1 is less than z and 1 is less than 1 is equal to 1, and we're in the middle, so 1 is less than a. And then 2, a is less than z for more or less the same reason. And of course, that means less than or equal to 2. And what that means is that actually a is in 1, 3, and z is not a lower bound for a. Oops. So we've derived a contradiction. We assumed that y was a lower bound that was bigger than 1. We found another lower bound that was bigger than 1, z, and then we checked, actually, Z is not a lower bound for this element of A of the open interval. So that's more or less how we do these sorts of calculations. And of course, we've done this little averaging trick a few times at this point. So hopefully you can see that it's a useful tool for dealing with these types of basic questions. So that's it for the introduction to the real line. In the next part of this unit, we're going to be dealing also with a few inequalities and a few other sort of immediate corollaries of these basic definitions, which will be used throughout